Hello, I'm Yipo Liu. Today I'll be introducing navigation of a self-driving vehicle using one fiducial marker. This work was done in collaboration with Hunter Schofield and Professor Zhenjun Shan. We are with the Department of Earth and Space Science Engineering, York University in Canada. Fiducial markers are planar markers that provide the environment with controllable and stable artificial features. They are widely used in augmented reality, human-robot interaction, and many other robotic applications. On the left side, we present some popular fiducial markers. However, in the real world, when the projected marker on the image plane is small, or the relative motion between the camera and the marker is fast, the perspective effects become weak. Then, the problem of twofold ambiguity that corresponds to an angle reflection about the plane and flips the z-axis in the camera's frame arises. That is, a marker could project at the same pixels from two different poses. The figure on the right side shows a sketch of the rotational ambiguity problem, which occurs very often in the real-world applications. To have a better understanding of this problem, let's watch a video. As we can see, the pose estimator is hesitating between two possible poses or solutions. Resolving the rotational ambiguity is crucial for visual surveying works where the control commands are generated based on the camera's measurements. Take our proposed framework as the example. The steering angle command mainly relies on the relative orientation between the desired viewpoint and the current location of the vehicle. Thus, the rotational ambiguity can affect the decision of whether to turn right or left. Once the vehicle executes the wrong turning decision, the navigation task then fails. Even worse, the ambiguity of rotation leads to the flipping of translation, which ruins the positioning directly. In this work, we present a navigation framework of a self-driving vehicle using one fiducial marker. Our unmanned ground vehicle is equipped with a wheel odometer and a camera cluster, which has a 360 degrees wheel. Moreover, our framework only requires one fiducial marker to work. As introduced previously, the main challenge of this work is the rotational ambiguity problem. Correspondingly, we propose an algorithm that resolves the rotational ambiguity problem based on sensor fusion of the camera cluster and wheel odometer. First, let's look at the multiple camera model. This model describes the mathematical relationship between the coordinates of a point in the 3D world frame and its 2D projection onto the image planes of the multiple cameras. Based on this model, the reprojection error of a given pose TVW is as follows. Thus, the pose estimation of the vehicle is to minimize the reprojection error of all the feature points on all the image planes, which is inherently a least square problem. And we adopt Levenberg-Marquardt algorithm to solve this problem. The initial values, that is, the two possible poses for the LM optimization, are obtained from solving the infinitesimal plane-based pose estimation. Note that so far we don't know which solution is closer to the ground truth. Next, I'll be introducing kinematics of our vehicle. We adopt a 3DOF bicycle model as shown in this figure. B and W denote the vehicle and world coordinate systems respectively. Given a steering angle of the front wheel, δr, the vehicle will turn about the turning point O with a turning radius, rr. The mathematical relationship among these values is given on the right side. In this system, δr is available from the steering angle recorder and the linear velocity of the vehicle is obtained from the wheel odometer. Based on these equations, the velocities of the vehicle can be measured. Now let's look at the sensor fusion part. Here we adopt a classical Kalman filter which is widely used in visual surveying. What I want to emphasize here is that the first three values of the observation vector x, y, and phi are obtained from the camera cluster and the last three values, Vx, Vy, and phi dot, are obtained from the wheel odometer and the steering angle recorder. Additionally, the system of our vehicle provides the function for data synchronization. It should be noted that in this discrete system, the prediction is a key point to resolve the rotational ambiguity problem at each sample step. Now we come to the most important part of this work, resolving the rotational ambiguity problem. Suppose that x hat is the a priori of sample step k. The first step will be finding the pose tw that associated with the a priori. Then we need to compute a feature level cost E. This cost is composed of two factors. The first factor, E1, is the reflection error which has been introduced. The second factor, E2, describes the error between the 3D coordinates of 2 points with respect to the vehicle coordinate system. Hence, the cost E is actually a sum of the 2D image space error and the 3D object space error. Then, we select the pose which has a smaller cost value as the unambiguous pose. On the right side, we present a flowchart of the proposed algorithm. At sample step k, we first find tw based on the a priori. Then we obtain two candidate poses by solving IPPE. Next, we can find the unambiguous pose by computing cost E and use this pose to update the filter. For the lateral control, we adopt the Ackermann steering geometry. That is, the steering angle is generated by a P controller. For the longitudinal control, we adopt a PI controller. Moreover, we'd like to add a remark to this work. The one-marker case is not an artificially difficult scenario. Even if multiple markers are set in the environment, there might be a moment when only one marker is observable. Since our framework is developed for one-marker case, it can be easily extended to multiple marker scenario. Finally, let's watch the test video. Here we present the comparison between our method and the default logic used in the APROTEC system. In the APROTEC system, the pose with a smaller reflection error is chosen as a true pose. We denote this logic by method A in the following. The objective of this test is to let the vehicle pass through some desired waypoints. As shown in the video, the vehicle successfully reaches the waypoints using our method, while the navigation task fails using method A. It should be noted that method A runs simultaneously with our method during the test. That is, the two methods share the same images frames as the input. For a fair comparison, we also apply a comment filter to method A. In these figures, method A is denoted by blue lines. Our method is denoted by black lines. The measurement from the motion capture system, which we take as the ground truth, is denoted by red lines. As shown in these figures, outputs of the method A and our method are almost the same at the beginning. However, when the vehicle starts to move, method A starts to select ambiguous pose while our method remains stable. As the vehicle approaches the marker, both method A and our method converge to the measurement from the motion capture system. This is because the size of the marker in the image plane increases as the vehicle gets closer to the marker, thus perspective effect is enhanced, and method A can also work. In conclusion, a navigation framework of a self-driven vehicle using only one fiducial marker is proposed. The rotational ambiguity problem is solved through computation of a novel feature level cost. However, there are some remaining fundamental challenges in the fiducial marker applications. For instance, marker detection failure due to motion blur. So now we are integrating a deep learning method into the application of the fiducial marker system. That's all for my presentation. Thanks for your attention.